hey, I have this powder. This is a powder of some nanoparticles. So I want to look into it very closely. So nanoparticles are very small particles. So I want to see how this looks like when I zoom in so many times. So I have an instrument which is called field emission scanning electron microscopy, and this is the sample holder. I will spread this sample of my nanoparticles into this sample holder by using this tape. This is a conductive tape, conductive carbon tape. I will paste this carbon tape in the sample holder, and then I will use this spatula to spread this sample into this sample holder. Then we will do the coating. We have to use very small amount of sample, and we have to spread the sample in a thin layer above this carbon tape. So this carbon tape is a conductive tape, and we need this conductive tape here because then the machine will give some electrons into this sample holder. So for those electrons to transmit or like to discharge into earth, we need this conductive tape, and above the conductive tape we are spreading our sample like this. So my sample is now spread evenly all over this conductive tape. So because this sample holder is very big and I have only one sample, I took a bigger carbon tape and spread my material all over it. So you don't need to use this much area of carbon tape and this much amount of material for normal analysis, but for the sake of showing, I am just taking it like this. So material is being deposited, spread on top of this carbon tape, which is pasted on the sample holder. Now this carbon tape is adhesive on both sides, so it can stick the material and it can stick itself into the sample holder also. Now this material is not conductive, it is a semi-conducting material, whatever my sample is. So it is because it is semi-conducting, and because I will be giving many electrons into this in this instrument, I need to coat the surface of this semi-conducting material with a conductive metal. So here in this instrument we are going to coat platinum. Generally platinum, gold and all are being coated to make the conductive layer above the sample if it is a non-conducting or semi-conducting sample. Now I am going to do the coating of platinum on top of this sample which is spread over this carbon tape. Let's see that coating. So in this system we used to use platinum metal coating, and this is the platinum coating system. This is a sputter coating system with a platinum target. This is the platinum target here, target material. About sputtering I will make another video. So this is the platinum target, and we will keep the sample holder inside this vacuum chamber. This is a vacuum chamber in this system. We will keep it inside, and there is a vacuum pump connected to this system, this sputter coater. So now I will turn on the system. After keeping the sample inside, I will turn on the system. So when I turn on the system, the vacuum pump will automatically start. Now the vacuum pump is running to make a vacuum inside this chamber. So now the pressure is high for this system. When it will reduce, it will show the pressure reading. Now it is 29.8 Pascal. So the pressure will reduce and come down to 3 Pascal inside this chamber. After that, we will carry out our sputter coating. Now the pressure inside this vacuum chamber is 3.2 Pascal. I can start the system when it is 3 Pascal, that is the recommended pressure for this. And my sample is not highly semiconducting. It is having a band gap of around 2.5 electron volt. So it is a moderately semiconducting material. So I need a thickness, the platinum thickness I need to make kind of a moderate thickness, not too much and not too small. So in this system I can make it a moderately thick platinum thickness on top of my sample by using a current and a time. So current I am going to use is 30 milliampere and time I am using is 120 seconds. I can change this time value. I am keeping it 120 seconds and then 30 milliampere current. And now the pressure is 3 Pascal. Now I can start the system. Like time is 120, 30 milliampere current. I am starting. Now you can see inside the vacuum chamber there is a color coming. There is a pink color coming. So this color is a manifestation of a plasma. So what happens in sputtering is that when we create vacuum and then an anode and cathode inside with some potential difference, the minimum small amount of gases present inside that one will ionize, and ionized gas is plasma. So the plasma will be generated inside this, and that plasma is responsible for, the ionized gas is responsible for creating this platinum coating by removing platinum metal from the platinum target, and those will be deposited on the sample. So now the color is coming platinum, this color is coming when the ionized gas, that is the plasma, will get consumed. These ionized gas ions, they will recombine and they will form gas back. At that time the color will come out. That is this electromagnetic radiation coming out of that reaction. Now it is going on, the coating, 30 seconds more. Now the coating is completed. Now I can switch off the system, and before opening this I need to wait for some time. So I need to let that the pressure should be back to atmospheric pressure, then only I can open this. We'll try. We'll wait for some time. Now the sample color has changed. Sample has been coated with platinum, and now we can do our analysis with the instrument. So now the instrument, so this is the scanning electron microscope. So the model number is JSM 7610F from Joel. Joel is a company from Japan, and in this scanning electron microscope, the main part is this electron gun, which is going to produce a beam of electrons by field emission, and then there is a vacuum chamber here, and there is then we'll be inserting our sample into the vacuum chamber. Then there is backscattered electron detector, secondary electron detector, and then we will be like, those detectors will help us to get image of our sample. So I will be using the secondary electron detector for my sample because that will give me the details I require, the morphology I require for my sample. Backscattered electron detector is generally required for atomic contrast and topography and other features. So I need the secondary electron detector image, so I will be using that. Now I will show you the instrument around little bit closely. Now this is the scanning electron microscope. It is from this company Joel. and the model number is JSM 7610F, field emission scanning electron microscope, and it is having, this is the electron gun which is there on the top, and then there is a vacuum chamber, and this is the side chamber which we will be using for insertion of the sample. And here there is our backscattered electron detector, and in this side there is a camera. This is for the camera. There was a small extension you are seeing, and on the other side here there is a secondary electron detector. We cannot, that is the extension that is being shown there on this portion. And then in the vacuum chamber, the ultra high vacuum that will be created by a turbomolecular pump and a rotary pump. So the turbomolecular pump for the system is underneath this main vibration isolated stage. So the instrument is under this vibration isolation, and turbomolecular pump is underneath, and the vacuum rotary pump is outside. And the electron gun require very high vacuum that is created by sputter ion pumps. So those are also there in the system. So the electron gun is always kept on so that will not be damaged. The system is connected to a computer. So this is a computer which we will be using to control the system, and we have different controls here which we will be needing to take images with this system. So I will insert the sample now through this chamber, and I will be showing you how to insert the sample. So this is my sample. I need to insert this sample into this vacuum chamber. So there is a side chamber here attached to this main vacuum chamber, which will be used for inserting this sample holder into the system. So first, now this side chamber, vacuum chamber is under vacuum, ultra high vacuum. So I need to vent this side chamber. So for venting, I need to click this button, vent. So there is a nitrogen gas supply connected into the system. That nitrogen will go into the side chamber, and atmospheric pressure will be there in this side chamber, and then I can open this thing and insert my sample. When the venting is completed, this will be like glowing continuously. Now this exchange chamber is vented and it is under atmospheric pressure. Now I can open this like this. I can open. So there is a rail where I can keep my sample holder. So in this sample holder, there is an arrow mark. So this arrow mark, we will keep it in such a way that this arrow mark will come on this side. So I'll insert the sample holder in this way. I'll insert it this way into this rail. I'll make sure that it is completely touching the ground and insert it in this way, and the arrow mark will be here. So and then after that I can close it. Like this, and then it will be in atmospheric pressure only. So I need to evacuate this chamber again back to the vacuum pressure it was in by clicking this. Now when I click this evac button, now this side chamber is being evacuated by the rotary pump. The turbomolecular pump is only going to evacuate this main chamber. So this exchange chamber will be evacuated by the rotary pump up to a low vacuum of 10 raised to minus 3 bar or something like that. After that, there is a door here that will be opened, and then turbomolecular pump also will try to evacuate everything. It will be like after that it will be a common chamber, and then vacuum will be like generated by the turbomolecular pump as well. So now you can see it is evacuated. Now you can see here in this computer, in this screen here, this is a layout of the system, and this is the main chamber, this is a side chamber, and this is the gun chamber. So now there is a door between this main chamber and the side chamber, the exchange chamber. Now after we click the vacuum and the vacuum pump got started and evacuated this side chamber, now the door has opened, and the entire main chamber and side chamber is under vacuum, and that vacuum pressure is now shown here. It is 3.0 into 10 raised to minus 3 Pascal. So for the system to be used, for us to use the system, the pressure is supposed to be less than 7.8 into 10 raised to minus 4 Pascal. So now the turbomolecular pump and the rotary pump is working to remove gases from this main chamber and side chamber, so that the pressure will be less than this 7.8 into 10 raised to minus 4 Pascal. When the pressure is less than that, we can start using the system. Now that the door is open, we can insert our sample from the side chamber. This is a sample, this rail whatever we have seen. So we will push that into the main chamber, and it will be resting on the sample stage in the main chamber. So then after that we can turn on our electron beam whenever we are ready with the pressure. Now I will insert the sample holder into the main chamber. So this is the lever which we will be using to insert our sample holder rail into the main chamber. So I will just use this lever to insert our sample. So I need to hold this way. There is a stopper here. I need to rest this rod on this stopper. It is being resting, and then I need to just push it like this up to here, and then after that I can take it back and keep it here. Now the insertion of sample holder into the main chamber is completed. Now you can see in the computer scene something is missing. Now in this screen you can see in the layout our sample holder. There is a sample stage here. On that stage now the sample holder is there. Sample holder is now resting on that stage. So in this we have to select the specimen holder we have inserted. So I have inserted this 32 mm specimen holder. I will select that, and my sample was powder without any height. So I need to keep an offset height depending on the height of my sample. Because my sample height was very much negligible, I'll keep this 0 only and then click OK. Now that our sample holder is on the sample stage, we need to turn on this camera. There is a camera attached to the system. That camera will give us a view of the inside of this vacuum chamber. So in this camera you can see that this is the electron beam outlet from the electron gun, and you can see a view of this specimen stage is also there. And we will use this camera to adjust the working depth or the distance between the sample stage, the sample holder, and the beam outlet. That will be called the working depth. So we will adjust that as 8 mm. Now I will click 8 mm and I will move the stage up. So the stage is now moving up. You can see the working depth is changing. The Z height of the stage is also changing. So the stage is having X, Y, R, Z and tilt. So it is a 5-axis stage, U-centric stage, which we can rotate, tilt, and we can even move in X, Y axis. It is going to 8 mm, and at 8 mm it has stopped. Now this is our sample holder on the sample stage, and this is the beam outlet. So in the periphery of this beam outlet there is one in-lens secondary electron detector, and other than that we have another secondary electron detector on the side of this. So we will subject electron beam into the sample, into the sample, and that the electron beams which we are going to give into the sample, that will take out electrons from the material. Those are called secondary electrons. Those secondary electrons will come according to the availability of electrons and the morphology, and from the number of electrons reaching the secondary electron detector from various places of our sample, that will define the morphology of our sample, that will define the photography or the photograph of our sample. We can see according to the number of secondary electrons going into the detector from each of the locations of the frame in the sample. So now we have adjusted the working depth to be 8 mm, and everything is now ready. Now the vacuum inside the chamber, vacuum pressure inside the chamber is 9.6 into 10 raised to minus 5 Pascal, which is very much less than our required pressure of 7.8 into 10 raised to minus 4 Pascal. So now we can close this window, camera window, and turn on our electron beam. So before turning on our electron beam, I can adjust the acceleration voltage of this electron beam. So this electron beam is created by accelerating electrons through this field emission gun. So the acceleration voltage, now we can change the acceleration voltage from 0.5 kV up to 15 kV for FESEM analysis. Now we need to be wise in choosing the acceleration voltage. If we use high acceleration voltage, the electron current, the probe or the electron current which is going to come into the sample will be very high. So that may be required for imaging materials without much of secondary electrons. We may need to give high acceleration voltage. But in normal cases, if we give high acceleration voltage, there is a chance that can burn the sample, and also underneath layers of the sample also will be visible if the acceleration voltage is very high. So generally good images is always achieved in low acceleration voltage. But if the acceleration voltage is very low, the number of electrons coming into the sample holder and the sample will be sometimes very small. In that case, we may not be able to focus the sample. So that is also a problem in low acceleration voltage. So acceleration voltage should be chosen in between. So for my sample, I can go for acceleration voltage of around 5 kV or lesser maybe. So I will choose 5 kV acceleration voltage and turn on observation. That will turn on the electron beam. So there is a shutter here that will be open, and the electron beam will fall into the sample when I click this observation on. You can hear a sound now. Now the electron beam is falling on the sample holder. Now itself you can see that there is something there on the frame. So we will manipulate now. Before that, I will show you the controls which we need to get a good image of our sample now. So these are the 3 controls we will be needing, exactly like the clutch brake accelerator of a vehicle. So in this, firstly I will talk about this thing. This is a specimen stage controller. So our stage, I told you, is a 5-axis eccentric stage. So we can move the stage in X and Y plus minus with this controls, and we can move it in Z-axis with these 2 controls. We can adjust the tilt and rotation with this controls, plus R, minus R, rotation clockwise, anti-clockwise, tilt in one positive direction and tilt in negative direction. So by using this specimen stage controller, we can align the stage in a particular angle, in a particular way, so that we can image even in different views, like isometric views, diametric views, and different views. Whatever kind of images, 3D images also we can take out of the system if you are good in this specimen stage controller. The next thing is this thing. This we will be using for focusing as well as moving around the sample. Moving around the sample by this jog wheel, and if you rotate this, you can use that for focusing, for fine focusing. So this is the main control which we will be needing to take image with the system. So here there is this magnification option, magnification. So now the system is in low magnification mode. We can change to FESEM mode or high magnification mode by clicking this. Then it will be turned off, this light will be turned off, and we can go to high magnification mode, and with this rotating wheel we can change the magnification of our image. And after that, after changing the magnification, this parts are actually required for focusing. So this is focus, and by rotating this wheel we can adjust the focus of our sample. We can focus and get clear image of our sample. This is for autofocus, and you can for focusing we need to use this three wheels together in this button on, so that astigmatism can be removed. There is astigmatism is a problem in which circular objects will be seen as elliptical either in x or y axis. So we need to correct astigmatism. That is why while focusing we will be using these three wheels together in stick on, so that we will not have any astigmatism and we will be able to focus our sample perfectly. So we will be needing this stick on and then these three wheels together for focusing. And for image to change the contrast and brightness, to get a good contrast and brightness, we can adjust those things with these two knobs. And here we have different scanning modes: quick view, fine view, RDC image. So these are different modes with different scan velocities. So our electron beam will be scanned in this frame. That is the name of the microscopy, scanning electron microscopy. So the electron beam will be constantly scanned over this frame of ours, whatever frame we are viewing, in a zigzag manner with different scan velocities. So quick view, there are two quick views with the system, quick view 1 and 2, which will have different scan velocities, and fine view, there are 4 fine views will have different scan velocities. And this is a reduced image screen which we can use for focusing. And this is for astigmatism correction. I told you while focusing we need to use this one. And this is for alignment. If you click this align, you can align the beam in x and y axis. While aligning, the wobble will be automatically on. The beam will be moved in xy in a wobbling manner, so that you can align it perfectly. So that for that purpose we can use this align button. So after you are done with magnification, focusing, contrast and brightness, adjust everything, then you can go to this fine view, and then when the fine view is completed, you can freeze the scan, and then you can go to this photo and click an image. That is how you will be saving an image. And here there is this auto contrast and brightness. So this auto contrast and brightness, ACB, is used when you are not able to correct the contrast and brightness to get a good image. You can click this auto contrast and brightness like autofocus, but generally we need to do it manually, and so that we will be getting one good image. So these 3 knobs are required, 3 controls are required for us to get a good image. So after keeping the sample inside the system, there is nothing we should do with the system manually. It is all about using these 3 controls to get a good image, and then after that saving that image in a JPG file format. And you can magnify with this instrument. In the low magnification mode, the magnification will increase up to 10,000, and with high magnification mode, the FESEM magnification mode, the magnification can be increased up to 1 million times. So you can zoom your object 1 million times, and you can get the image. So we will be seeing our nanoparticle. By using these controls, we will focus and we will magnify to one particular magnification. We will focus, we will adjust contrast and brightness, and we will take the photo. So this is the software which we will be using. So firstly, I have adjusted the acceleration voltage to be 5 kV, and the working distance is set to 8 mm, and everything else is now correct. Now I just need to see the image in the frame in the bigger screen. So I will go to full image. I will click this. So now I can see the frame, the complete frame, and something is already visible, but it is not clear. It is not zoomed enough. So and you can see something round here. So this round, now the magnification is 25, and in 25 magnification, that is the minimum magnification possible. So whatever you are seeing, this round thing is the circumference of this lens. So wherever, through whichever way the electron beam is passing, that iris, that's what you are seeing here. So we will zoom in little bit, and that will be gone. This is the sample. So now the system is in low magnification mode. In this low magnification mode, we can increase the magnification up to 10,000. So it is recommended to increase the magnification gradually, and then focus like that. So I will increase the magnification from 25 to a little bit higher by using this magnification knob. I will increase the magnification like this. Now the magnification is around 100. So now whatever is there in the frame, it is little bit more bright, little bit more sharp, it's not focused. So I will just adjust the focus first by using this focus knob, by rotating it like this. I have adjusted it to be like this much. It is now a little bit focused. Now I can reduce the brightness with this knob as well. Now contrast is okay, fine. And now I will magnify again. I will keep this in the middle. By using this knob, I can move the area whichever part of the sample it is seeing, the frame is seeing, and then I will hold this to move, and then I will magnify with this magnification knob. Maybe up to here I will magnify. Now I have magnified up to 500, and now again I need to focus. For focusing, I will use the focus knob like this. I have rotated and it got focused. Now contrast and brightness okay. So I will magnify again now up to 1000. Now I need to focus a little bit more with this knob. It is focused. So this low magnification mode is generally being used to locate the region of the sample where you need the image. So for my sample, I don't care about which area. So I will just select, like, if one person needs this type of one thing, so you can focus first. You can magnify up to 1000, focus, and then you can move around and see the location, find the location, and then you can magnify there. I don't care. I am just magnifying here up to 1000 and deciding that this is the location where I want image in. So I will focus a little bit more after going there. So up to this I did in the low magnification mode. Now I need to, my particles are very small. Those are nanoparticles. So I need to zoom more. This is zoomed 1000 times. So I need to zoom more. So for zooming that, I can only zoom up to 10,000 in this low magnification mode, but I can zoom up to 1 million times in the FESEM mode. So after reaching this 1000 magnification with the low magnification mode, I can click this low magnification to be disabled. Then the system will go to high magnification mode or the FESEM. So you can go from this low magnification mode to high magnification mode also by going to the standard view, whatever view we had before, and then selecting FESEM, column mode FESEM from here. You can just click and then the instrument will go to SEM mode. Now the instrument is in SEM mode and you can come back to full image. So now in this SEM mode image, whatever frame you are seeing, it is somewhat dark. I cannot see anything. So firstly I can increase the brightness and contrast little bit, just to make it like this, and then I can, this is the minimum magnification we have, 600 in this SEM mode. Then I can try to focus. I can try to focus by rotating the focus wheel, and when I rotate I got one image. I got something. So here when I rotated this focus wheel, you can notice that the working depth is changing. So earlier we kept the stage at a particular height of 8 mm from the beam outlet, but now when I rotate this focus wheel, the working depth is again changing. This doesn't mean that the stage is moving. It means that the electron beam is having different convergence, and it is being focused at different heights from the beam outlet. So when the electron beam is focused at around 10.4 mm from the beam outlet, we are able to see the sample, the image. Now if you have noticed, in the sample holder, even though the sample holder was the outside periphery of the sample holder was at a particular height, the region where we kept our carbon tape, it was little bit inside, 2-3 mm inside. That is why even after keeping the distance between the sample holder and the beam outlet to be 8 mm, now the beam had to be focused at 10 mm, 10.4 mm from the beam outlet. So that additional depth we had in the sample holder, that is being covered here. Now you can see the image is kind of focused. So I will now go magnify up to maybe say 1000 or something. Maybe I will magnify up to 2000, and now you are seeing a blurry thing. So I will adjust the contrast and brightness little bit like this, so that it will be a little bit visible. Now I will be focusing this like this. So I am rotating the focus wheel. Now if you observe, it is just like rain. So something is like some line kind of thing is happening in this direction now. Another line kind of thing is happening in this direction now. So that is astigmatism. So our image is being stretched in X and Y axis because of astigmatism. So what you need to do to get a focus now is to firstly avoid this stretching in different axes by rotating this focus knob. So I will rotate from this portion where there is stretching here. I will rotate and rotate up to here where there is no stretching. Then I will use this XY knobs for this astigmatic correction, and I will rotate until I get no stretching and better focus. Maybe somewhere here. Then I will rotate the third one also like this, like this, like this. Now when I rotated the third one, it got improved. Now I will again use the focus knob. You need to use these three in a cyclic manner. So I again use the focus knob to get the focus right. And then I will use the Y knob again to focus. Then I will use the X knob again. Like this we will be using. Now after that I will be magnifying again. Maybe up to here to 5000 magnification I magnified. And now I am doing focusing little bit. There is now, you can see stretching is there in this axis. So I will avoid that stretching. Now stretching is in this axis. I will go to the middle of that where there is no stretching. I kept in the middle so that there is no stretching. And then I will rotate this Y knob to get focus. Now it is not focused, becoming a little focused. After that, X knob, like this. Now it is little focused. Now I can just like reduce the contrast little bit and increase the brightness little bit. Now you can see something. Now I will magnify again. Magnify it again up to 15,000. So here I will focus with this focus knob. There is some stretching. I will go, but there is no stretching. Maybe up to here. And I will use this knob. And then this one. I kind of magnified up to 15,000 and then try to focus. Now I will go for better locations in my sample. My samples are some nano wires. I will choose this area somewhere here. I'll choose this area and try to focus. Now I magnified up to 25,000. Then after that, I will try to focus with the focus knob. If you rotate more, you will get an idea. You will I am just rotating too much this knob and then going to the middle where it is somewhat focused. And then I am going to the other knob. This is not at all focused, somewhat focused. And then I am rotating it again in one direction. Like this. And then this one. So I went up to 25,000 and I am trying to focus this by this focus knobs. I tried my best to focus the image in 25,000 magnification with these three beams, but still the focus is not satisfactory for me. So I feel that the acceleration voltage I am using, that is not sufficient. So I will increase the acceleration voltage to 15 kV. So now when I change the acceleration voltage, when we change the acceleration voltage, the energy of electrons will change, and that will change the wavelength of electrons, and that will change the focal depth. So I need to adjust this focus again, the working depth again. I am rotating this wheel now. So now you can see the image is little bit more better. If you see, the image is somewhat better in this high acceleration voltage. So what I do generally is I magnify up to the maximum possible magnification, that is 1 million. I can magnify up to 1 million, but that is the specification limit of the instrument. Generally up to that we don't generally go. So I generally go up to 100,000 and then try to focus on that magnification. I will try to look for edges. Maybe you can notice the edges of this, whatever I am seeing, sharp edges I am making. I am just defocusing it so that I will be able to know which rotation, what rotation I need to use, which angular position will give me the good focus. Not changing that much. I can reduce this contrast and brightness so that I will be able to see the boundaries of those particles in a clear way. This feels like a little better. Here, this looks little better. So I came up to 100,000 just to focus. So now I will go back to a low magnification and take the image. So this strategy is required when if you want to take an image of very flat surfaces. If you want very good focus, it is better to go for high magnification focus and then come back. But this is not going to work when you have a sample with irregular height. So I am just coming back to 50,000, 40,000 and coming back to 20,000 and I will take an image. Now the scanning mode is quick view. So in quick view the scan velocity is very high, so the image is not coming in very good clarity, but this quick view is used for focusing. Now I will go for fine view by clicking this. So there are 4 fine views. I will change to CF2. Now this CF is enabled and there are like this is the slowest scan speed. So the image will be having good clarity. Now the scan is going on. Electron beam is scanned in a zigzag manner. It is not exactly in a zigzag manner, it is exactly like a raster scan, which is like line by line scan will be carried out. So if I don't click this freeze before the scan completes, the scan will happen again. So I need only one scan, so I will click freeze before this completes. So this will be blinking. When this scan completes, it will be glowing continuously. Now it is glowing continuously. I can click this photo and just save the photo of my particle, nanoparticle, in my folder. So I saved my image, this image in a JPEG format. So I will now click on this freeze again to unfreeze the scan and then I will come back to the quick view. Now I will try to focus a little bit more. This focus is not satisfactory. So I will try to focus a little bit more. magnified and then focused. Now I will take an image again at 25,000. Hopefully this will have better clarity. I will click freeze. Now you can see there is a scale bar here. This is a scale bar with 1 micrometer length. So it means that whatever you are seeing here, if you compare with this scale bar length is 1 micrometer. So these things are in this order of 1 micrometer. So probably these things are less than 1 micrometer length, and I will show you how to get the exact length of these particles. Now the scan is completed, the freeze is glowing. I will click photo and save. The second photo is also saved. Now freeze again and come back to QQ. And now I will go from this portion to some other portion. Maybe I will take an image, like these are all nano wires. So I will go to, this is a big chunk of nano wires, so many nano wires. So these nanowires are broken. These are broken into small pieces. I remember that it is to be a little bit bigger, longer. So because I spread the sample, you are seeing that like sandwiched kind of thing is there. Now I will go to maybe some place like, see, maybe here. I will go here. Here I will go. This one. I will magnify a little bit. I need to focus this because now this is at a different height. So that is why I had to focus it again. I am focusing it now. Like this. I am just looking at the edge of that particle. The edge is being distinct, it means that it is focused. It's okay. I will just maybe magnify a little bit more up to this much. Try to focus a little bit more. Then demagnify up to my 25,000 and then I will go to fine view. Maybe freeze. Now I will just put some scales, some dimension scales with the help of these things in all these nanoparticles, nanowires. I will do something like I will put this thing like this from here to here. This is now 750 nanometer nanowire, and maybe like some other nanowire if I need to see the length. Something is really broken. Like see, if you see this is not that long. This is only 300 nanometer length. The width of this nanowires are somewhat same. Every nanowires are having similar width. They may be having width of 0.1 micrometer, means 100 nanometer width. So these nanowires are having an aspect ratio of around 10. Length is 10 times, at least on an average it is 10 times of the width. So like that, like this way, you can get the length of different things by assigning this arrow mark things. Also, you can go for the ruler in x and y axis. You can move, and then that is little bit like not that much convenient. Than this, you can do for any angle, anything. So after that, you can click this again and delete if you don't want. If you need to open this again, texting, then you need to click this, delete, click this, delete, click this, delete, and close this. Now I will go back to, I'll save this, and I will unfreeze and come back to quick view. Then maybe I will try to zoom it maximum, try to see what is the maximum zoom I can get before winding up. The maximum zoom it is possible by this instrument, maximum focus that is possible, zooming possible up to 1 million times, but we cannot focus at that magnification, it will be blurry only. I am trying to focus at this magnification also. Now zoom and see like that. So this instrument, like this way, you can put your whatever kind of sample, metal, your semiconductors, your biological sample, whatever samples you have, you can put that sample in the sample holder. You can keep with a carbon tape, and then you can use this instrument to take images of those kind of things, whatever it is. So here you can see my nanowires are little bit more longer and they are kind of spread around. You can see here they are more longer. So this place looks little bit better than the other place. I will focus little bit. Maybe I can take one more last image at 10,000 magnification. I will click freeze. Now this looks little beautiful. All the nanowires are densely and closely arranged. Now if I go back to standard view again, and if I select this LUT and then take this up, this click this, then I can adjust this two things to adjust the contrast and brightness. I can move like this, and then I can, by that way, I can adjust the contrast and brightness of the image. If I want this kind of like color, this is like the red color is coming from regions where more electrons are coming into the detector. This is 16-bit colors, this is 128 colors. So different color spectra is also possible, but nobody will be taking this kind of images. We need this kind of contrast, different contrast, black and white images only we can get. So new FESEMs can provide even colored images also. Not the actual color of the particles, but whatever some colors can be assigned. So this image is now, I can just save this image, the fourth image. I save the image, come back to freeze and quick view. Now the analysis, whatever analysis I have done, it is satisfactory for me. So I will just talk about something. So there is one recipe column here. So if you have different type of samples, you can use these different recipes to get predefined acceleration voltage, the column mode, SEM or low magnification mode, and the electron probe current, how much of number of electrons will be coming down, and what will be the magnification and everything, working distance, everything. You can be like predefined things can be got from this kind of recipe. So I use manual recipe, my own customized acceleration voltage, magnification, and the column mode and everything. So now my analysis is completed. Now I will do is switching off the observation. That will switch off, that will prevent the beam from coming down. So now you can see the shutter is closed. Now the beam is not coming. Now beam is off. Now I will come back to low magnification mode, and I will reduce the magnification up to 25. That is the minimum magnification for the system. I will keep it in minimum magnification. Now I will turn on the camera after that, and then I will click either specimen exchange or home position. Both are having coordinates of x0, y0, r0 and z38 and t0. So I will click home position, and then the stage will go back to 0, 0, 0, 38, 0. From that point I can take the sample holder back through the lever, with the lever. So it is now going on. When the sample holder will be on that location, XYZ TR location, this specimen exchange and home position will be blinking green. So now it is moving. Now you can see specimen exchange is now green. So the sample holder is now in the exchange position. So now I can take that back, the sample holder back. I can close this camera and take the sample holder into this side chamber. Now I will use this lever to take out the sample holder. So I will move this lever into this stopper. There is a stopper here. I will rotate this 90 degree and I will just rest on the stopper, and then I will just push it like this. Up to here I will push, and then I can take it back like this. Then I will keep it like this. Now the sample holder is in this side chamber position. Now after taking it from the main chamber up to here, now I can click vent. If after clicking the vent, the door will be closed and nitrogen gas will be flown into this side chamber to make it into atmospheric pressure, so that I can open this and take out the sample. So I will click vent. the software, the vent is blinking. The vent and evac controls can be done from the software also, and through these switches also. So now you can see the side chamber in the layout is in white color and the door is closed. Now when the vent will be completed, there will be glowing green in the software and in this button. Now the vent button is glowing, means that this side exchange chamber is completely vented to atmospheric pressure. Now I can just open this door and take out my sample holder like this way, and then I will close this like this, and then I will evacuate and keep it in evacuated conditions. Otherwise there is chance that this chamber will be having dust and other gases going in. So the system, the side chamber and the main chamber will always be in evacuated condition. So after I click this evac, this will be evacuated to a low vacuum pressure by this rotary pump, and the door will open, and then both the side and main chamber will be evacuated to ultra high vacuum by the combination of this turbomolecular pump and the rotary pump. Now the analysis is completed, and system is now the electron gun will be running all the time, and the turbomolecular pump also will be running all the time to keep the vacuum pressure inside constant and very low ultra high vacuum. Now we don't have to switch off the instrument, we just need to minimize the software, whatever software you have been seeing here. This software we will just minimize, and then that's all with the analysis. So I'm just minimizing this software. Before leaving, I will just show the image I have captured. So this is the folder. This image was not having good resolution, good focus. This image came little good. So this is cadmium sulfide nanowires of some 100 nanometer thick diameter and some 1 micrometer plus length. So like this we can image any kind of materials, whatever kind of samples you wish to see closely. After zooming so many times, you can see through this instrument. So I will close it. So I hope you have got some idea about this instrument and how we can get good images of some very small things by this instrument. So if you have more information about this instrument than me, you can share those information with me if you wish. And if you want to know more about this instrument from myself, you can contact me through my given details, and then I'll be happy to explain about some things about this instrument. So in our department, Center for Nanotechnology at IIT Guwahati, we have this clean room facility for we have different instruments here. So this FESEM is actually being used for another purpose also, that is for electron beam lithography. So we have an attachment here that will be used to move the electron beams in X and Y and create patterns in nanoscale. So this instrument is FESEM as well as electron beam lithography instrument. You can use this for imaging and you can use this for patterning in nanoscale. By using some electron beam resist, you can pattern substrates and get nano-sized patterns. And I couldn't talk anything about backscattered electron detector. So backscattered electron images are very rare in case of FESEMs. So people don't generally go for backscattered electron images. So for those kind of for topographical and other details, atomic contrast details, we generally go for backscattered electron detector. So the backscattered electrons are electrons which are coming back after being incident on the sample whichever the electrons which are coming directly back, whichever are scattered and reflected back, those are called backscattered electrons. So to get a good image with backscattered electrons, those need to fall rightly on normal to this detector, exactly normal to this detector. So you need to have a very good focus, alignment, everything to get good image with backscattered electron detector. And then that will be giving you details about the atomic contrast, different atoms, and maybe height difference, the topology details and everything. So we don't have any electron EDX detector, energy dispersive X-ray detector. We don't have any X-ray detector here in this system. So because of that reason, we are not able to catch any this EDX patterns and images which will give us elemental contrast. We don't have that, and that's all about this instrument.